All right, so we're going to look at a specific application of electric fields. And actually, this isn't really more of an application. This is the foundation upon which modern electric fields is governed. So there are these set of four equations called Maxwell's equations that govern all of electricity and magnetism. It unifies electricity and magnetism together. Gauss's law is our first equation that we have encountered that is one of Maxwell's equations. So with Maxwell's equations, we can explain all electromagnetic phenomena. And so here we're going to have to simplify things down a little bit because to truly use Gauss's law, we need calculus, and we don't have that. But Gauss's law is necessary in order to help us with all of these charge distributions that are not point charges and parallel plates. We can use other methods to figure those out. So we're going to see kind of how this works. We're not going to dig as deep as we would in a calculus-based course. This gets kind of 3D visual wonky, so do the best to kind of go along with it. I've got some concrete examples here that will help. And just realize that if you do go outside and look up Gauss's law, you're going to find a lot of stuff that's very calculus intensive. We won't do anything that requires calculus. So in order to talk about Gauss's law, we first have to define electric flux. So we've used electric fields to kind of visualize the fields and where the fields are stronger and weaker, but how do we calculate that? So flux is a way to count the electric field. Now, we're not actually going to sit here and count field lines. I'm not going to go, oh, 1, 2, 3, 4, 5, 6, 7, 8, 9. That is not what we're doing. When we say count, we're looking at kind of a relative image. Because I know that I could just keep adding more field lines, and there's nothing wrong with that. Because we're just using a representation for the number of field lines. So when we talk about counting, we're looking more like at a density idea. Where's there more field lines relative to other locations? So in order to do this, we need to find a surface. The flux is based on some sort of surface. So we often, for example, talk in atmospheric science, which is where I came from, the study of the Earth, the atmosphere. We talk about the solar flux, the flux from the sun. How much sunlight are we receiving? And that's based on, under the assumption that like the Earth is a sphere. And so it's the surface area of the Earth that is receiving that. And so the whole Earth could be a portion of that surface area. So we have a flux of sunlight through the surface of the Earth. But we don't always need a physical surface to visualize fields. So this surface is something that we invent in our heads that doesn't actually exist. But for right now, you can picture taking a piece of paper and holding it up in front of an electric field so that the field lines are actually penetrating that piece of paper, if that kind of helps you out. So what we want to do is figure out how many field lines are entering or exiting this paper. So I could count, and there's 9 of them. So the flux is going to be higher the more field we have passing through. To quantify that, we're going to use kind of the surface area, because the bigger my surface, if I have the same number of field lines, that's actually a weaker field. So it's like the product of the strength of the field and how many of the field lines are passing through, kind of conceptually. So we can't actually count the number of lines, but we can picture that that's essentially what we're doing. So my A here is perpendicular to my electric field. Picture that the surface area is a vector. The surface area vector points perpendicularly out of the surface. So in this case, my surface area vector is directly parallel to my electric field because it's pointing out away from that surface. The flux in this particular example would be E times A. So we're using capital letter phi, which I would draw it like that, with a subscript E for electric flux, because we could have solar flux, we could have magnetic flux. And that is equal to E, which is our electric field strength, times A, which is the surface area. So that is the simplest case. But if we tilt this surface, the field hasn't changed, but I can see that these three lines down here at the bottom are no longer passing through my surface. So my flux has decreased. And the amount that it decreased by is going to be related to the angle. I can see also that my surface area is no longer parallel. It would be coming out at that angle. And that angle right here is going to be related to the same angle right there. So if we were to draw that out, using those angles, remember that normal means perpendicular in physics. So the A vector is going to have a magnitude equal to the area of the surface and a direction that is perpendicular. So we can see that there is an angle theta, and you could do a little geometry to prove why these two angles right here are the same, but they are the same, is going to be what matters. So that amount of area is going to be A cosine theta. Because if you were to look right here and make a triangle, oh, wrong triangle, and drop down right here. So if that is my vector A, the portion of A that is parallel to my electric field would be A cosine theta. Okay, because I'd have a right triangle here. A would be my hypotenuse. The adjacent side would be parallel to E. So that's where this A cosine theta comes around. So that would be the portion of the surface area that is in the same direction as the electric field. Okay, the portion of the surface that's perpendicular to the field, but the area vector that is parallel. It's a little wonky. So because A is perpendicular to surface, the amount of A parallel is that A cosine theta. Okay, so A parallel to the field. So the portion of A that is parallel to the field is A cosine theta. So A parallel is A cosine theta. So our flux is not actually based on A in this case. It's based on EA parallel, because only the portion of the field that is parallel to A is going to contribute. So we end up with our flux being EA parallel, which is going to be EA cosine theta. Now, if you were to take a calculus-based course, we would introduce the dot product at this point, which would be E dot A, and our flux is equal to E dot A. But we're not going to work with dot products. We're not doing vector calculus. But in case you see that, that's where that's coming from, is this dot means take the components that are parallel to each other. For example, work is technically force dot the displacement vector. So normally we just do F parallel to delta X because we want the parts that are parallel to each other for work to be done. So I'm just giving you that, not because you have to know it, but in case you're looking at resources and you start seeing this dot product, and you're like, what? Where is this coming from? So that means our flux is going to be EA cosine theta. So I can see that as my angle theta increases, then I'm going to have less and less of my surface area that's parallel. So if my surface was actually here, then my A vector would actually come out perpendicular and I'd have no flux. Because if my surface is parallel to the field, I'm going to have no flux. If my surface is perpendicular to the field, I'm going to have maximum flux. Now, what happens if our surface actually has more than one face because it's a volume? Then what ends up happening, oh, this is a little out of order, is that we need to count up every surface. So you would do this with calculus, is really what it would do. You would take every little infinitesimally small piece of the surface and you would find the flux through each tiny piece. You'd add it up. That adding it up is called integration, and you would do that. Well, we can't really do that, and we won't have to for our purposes. But what we do have to do is we have to add the flux for each surface. So my flux here is basically the flux for surface 1 plus the flux for surface 2 plus the flux for surface 3. And I'd have to add those fluxes. But flux can be positive or negative when you're dealing with a volume, okay? Because if I look on this side, on this surface right here, those field lines are exiting the surface. If you picture the backside, which you can't really see, the field lines are entering the backside. So we count field lines that are going out as positive and lines that are going in as negative. So exiting is positive, entering the surface is negative flux. And I'll show you a simpler example kind of here in a little bit. We're just kind of talking conceptually. So this example surface has 3 surfaces. Oh, let me clear that. So we have the circular front, we have the circular back, and we have this side that kind of wraps around. Those would be our 3 surfaces that we'd have to consider. So we'd have to have the flux for each. This would be really complicated with it all tilted at an angle. You won't see anything quite that complicated. We're going to stick with simpler geometric shapes and situations where we can either be directly parallel or directly perpendicular. So the surfaces are used as a visualization tool. So picture that we have the electric field due to a positive point charge. So this is 2-dimensional, but these also go out 3-dimensionally in all directions. This is making vectors pointing out 360 degrees away from my positive charge. If I want to visualize the flux, I can put any surface around this. And we're generally going to use 3-dimensional volumes, which will relate to Gauss's law. So, for example, I could put an imaginary sphere that is centered on the point charge. And then what you can see is that there's symmetry going on. My sphere is very similar to the shape of that field. And all of the field lines are exiting the surface. So if I look, every single one of these field lines is exiting that surface. This tells me that there is a positive flux through that surface. Now, what if I had a negative point charge and I put that same sphere in place? Well, now all of these field lines are entering, okay? So that is now negative flux, okay? The field lines are entering the surface, so that is negative flux. Now, what happens if we say replace that sphere with a cube? Now, technically, my field lines are all still entering, so I know that this is going to be a negative flux. But this flux would be very difficult to calculate because every little piece is at a slightly different angle. Also, some parts of the cube are closer or further away from other parts. So we're going to have issues if we tried to calculate the flux on this one. We'd have some issues. So a cube is much better for something like a uniform electric field. So we're going to do this example. So we want to find the net flux through a cube whose faces have a surface area A if it is placed in a uniform electric field of magnitude E. So picture the setup here. This electric field is going through the whole surface. It's uniform. So I'm only showing a few of the field lines, but these field lines are everywhere. And all these field lines are constant in magnitude and direction. So no matter which part of the surface I look at, I know that the electric field has the same value and is pointing in the same direction. This cube has 6 surfaces. So we have to find the total flux. We have to look at each surface. So that's what we're going to do. We're going to break it down by surface. So the left face, if I was to draw the electric field, it's pointing to the right. Now, we have to look at the outside of the cube. So the surface area, the outside of my cube on the left, is pointing to the left. So the outside of that cube faces left. So my electric field and my acceleration, my surface area in exact opposite directions. If you were to do EA cosine theta, our theta is going to be 180 degrees. If you calculated cosine of 180 degrees, you would get -1. So our EA is going to be negative that also makes sense because on this face, my field lines are entering. So do I really need to calculate the cosine of 180 degrees? No. I can just look and know that because my E and A are parallel to each other, that my flux is going to be E times A, and that because it's 180 degrees and they're in exact opposite directions and my field lines are entering, because my field lines are entering that surface, that's going to be negative. So the flux through the left side is a negative E times A. Now if I look at the right face, if I draw my A and I draw my E, my A is coming out to the right now in the same direction as my electric field. If I were to do EA cosine theta, my theta in this case is 0. Theta cosine of 0 is 1. So this is going to be E times A times 1, which is just EA, which is positive EA, which I can also tell because from this surface, all of my field lines are exiting the surface, which also means I have to have a positive flux. So do I really need to calculate the cosine of 0? No, I could just see that because my E and A are parallel, or because my field lines are exiting, that is going to be a positive flux. Now, oops, wrong way. Look at the top. So if I look at the top face, my E is to the right. My A would be pointing straight up. They're at 90 degrees to each other. If I was to do EA cosine theta, theta is 90 degrees. Cosine of 90 is 0. So this is going to give me 0 flux. Okay, so there's no flux coming through the top. If I do the bottom, also 0. If I do the back, A is pointing into my screen, so that's what that X is showing. This X shows into the screen. A dot with a circle around it would be out of. You're going to see this a lot more in this class than you might have in your 1401, because we're going to be much more three-dimensional. So that is also going to be at 90 degrees. So no flux. And the front, that A is pointing straight out of the page. Our E is to the right, so those are also at 90 degrees, so no flux. So those sides, top, bottom, front, and back, have no flux. So all we have to do is look at the left face and the right face. So our total flux is going to be the right plus the left. Our right was a positive EA. Our left was a negative EA, so our total flux is 0. So this is a big general rule. If the number of field lines entering a surface equals the number of field lines exiting a surface, then the flux is 0. So if I look at this surface, I have 1, 2, 3, 4, 5, 6, 7, 8 field lines entering, and 1, 2, 3, 4, 5, 6, 7, 8 field lines exiting, so there's no flux. So you can always look at an image of the field lines and the surface and be able to predict what the flux is going to be, whether it's positive, negative, or 0. It might be harder to calculate the actual value. So here's another example. We have a dipole. So this is the electric field for the dipole. So we can see that the field lines kind of curve around, going from positive to negative. We want to find the net flux through a sphere. And I'm going to center that sphere on that dipole. So here's my sphere. So if we count field lines, we have one, oh, those are inside. We got to be careful. We're not looking at the ones inside. That's a different example. Okay, so we have an exiting here, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 field lines exiting, and 1, 2, 3, 4, 5, 6, 7, 8 field lines entering. So even though this field is very non-symmetrical, okay, it would be very difficult to do any sort of flux calculations like we did with the cube. I can tell that there's no net flux because the field lines entering and exiting are the same. So there's a pattern. I don't know if you figured it out. So if the net enclosed charge is positive, the flux is positive because you'll have an excess of, not really an excess, I like the net, a net number of positive field lines exiting. If your net enclosed charge is negative, the flux is negative because you'll have more field lines entering than exiting. And in both of these cases that we looked at, the cube and the one with the dipole enclosed, we were enclosing no net charge. The electric field, that was just a field. There were no charges inside of that cube. In our dipole, we had an equal number of positive and negative, so our total charge enclosed was 0. So this is the foundation for Gauss's law. So Gauss's law mathematically says that if we sum up the flux of every surface, okay, that's what this is telling us. We sum up the flux of every surface, which was our EA cosine theta. We're adding on this part on the right here. And that our total flux, our net flux, is equal to Q enclosed over E naught. This E naught is that permittivity of free space we've seen a couple of times now. And Q enclosed is the net charge, the total charge enclosed inside, with positives and negatives can cancel each other out. So Gauss's law says that the electric flux through a closed surface is equal to the ratio of the enclosed charge and the electric permittivity of free space. So if you can calculate the flux, if it's equal to 0, there's no enclosed charge. If you calculate the flux and it's positive, our Q enclosed is positive. And our ability to actually calculate the flux can then give us ability to actually calculate the charge. And that gives us a way to use flux to calculate enclosed charge. Gauss's law applies in every situation, because there's always going to be some sort of hypothetical surface that you can create for the craziest, wildest distributions. But it's, for our purposes, and even if we did have calculus, it's only going to be useful for situations that have a very, very high degree of symmetry, kind of like the sphere. We can't do something with like the cube around the point charge. Like, there's no way for us to do that with our skills. That's what computers are for nowadays, right? So one thing we're going to have to do in order to do Gauss's law is create that hypothetical surface. Now, the surfaces that we use for Gauss's law are called Gaussian surfaces, and they are surfaces that are fully closed, so they cannot be open. So, for example, your Gaussian surface can be a sphere, but it cannot just be a circle. This guy's a toroid. This one's kind of fun. Toroid. It's kind of like a donut. So it is technically fully enclosed. Or we've got a cube. That one's not that bad. A cylinder is also a really common surface that we're going to use. What it cannot be is it cannot be like an open hemisphere, although it could be a closed hemisphere as if it was closed like that. It's not going to be an open plane. It has to be something that closes entirely back in on itself. So you have to fully enclose it. But while you can use any closed surface, you're going to want to choose something that has symmetry with the field. So here's a kind of a fun conceptual example. So what we're going to do is we're going to look at these 6-point charges. We're going to assume that these are closed surfaces. Surfaces A, B, C, and D are closed. So this means they meet that 3-dimensional. So you can picture them being like these like egg-shaped things that are coming out 3-dimension, like 3D closed surfaces. They're not circles. They're not ovals. They're like ovoids, right? They're spheres. Like A is actually a sphere. Picture it's a sphere. So we want to rank the electric flux through each surface in order from largest to smallest. So Gauss's law basically tells us that our flux is equal to Q enclosed over E naught. Now I'm taking out the middle part here, which is that you take your EA cosine theta and you sum it up for every part, because that's not necessary for this part. That part of the equation is necessary if we want to actually calculate the flux, not knowing our enclosed charge, or calculate the electric field, is where that's going to come into play. So with this information, if we want to rank the flux, we really just have to rank the enclosed charge. So Gauss's law is kind of cool because it can allow us to rank the flux just by the enclosed charge. So looking at surface A is enclosing positive 5 microcoulombs, positive 9 microcoulombs, and negative 9 microcoulombs. So the positive 9 and negative 9 will cancel them out. So the flux through surface A is going to equal 5.0 microcoulombs divided by E naught. So we could actually calculate that flux as needed. We don't have to. Then if we look at surface B has the positive 9, the positive 1.0 microcoulombs, and a negative 10 microcoulombs. So positive 9 plus positive 1 is 10, minus 10, that's actually 0. So the flux for B is actually 0 because there is no net enclosed charge. There's enclosed charges, but when you add up those charges, they add up to 0. C has the negative 9.0 microcoulombs and the positive 8.0 microcoulombs. So that is going to give us negative 1. So our flux for C is going to be negative 1.0 microcoulombs divided by E naught. And then D is enclosing everything. So if we start at the top, we've got positive 1 and positive 9, which adds up to 10, which cancels out with the negative 10, so that goes away. And then we have a negative 9 and a positive 8, which simplifies down to a negative 1. So we have a positive 5 and a negative 1. That gives us the flux through surface D is going to be a positive 4.0 microcoulombs over E naught. So if you were to rank from largest to smallest, and remembering that negatives are actually smaller than positives, unless it asks for magnitude. If it wanted magnitude of the flux, then it wouldn't matter which were positive and negative. It just wants the flux. So our largest flux is A. And then our next largest is D. And then 0 is actually bigger than negative 1, so that's going to be B. And then C is the smallest. Now, if it asked to rank the magnitude, that is a different question. That you would ignore the positives and negatives, and that would be A is bigger than D, which is bigger than C, which is bigger than B. So 0 flux would be the smallest in that case. All right, so you just have to be careful. This is asking just for flux. This is asking for the magnitude of flux. Ta-da! All right, so now we have the opportunity to use Gauss's law to actually find the electric field of all sorts of different types of charge distributions. Now, to do that, we want to not have to solve this really at all. This is actually even the simpler version than the calculus-based version, which is the correct version, which that's an integral. Okay, so that's why there's an integral here. I didn't delete that. We don't want to solve an integral at all. We don't even want to solve the little bit. We don't want to worry about the cosine theta. So what we want to do is we want to select our surfaces so that they are either parallel or perpendicular to the field. So we want to choose our surface so that our electric field is either directly parallel or directly perpendicular. So cosine theta is either going to be 0 or 1. So if our electric field is parallel to A, then EA cosine theta is E times A. And then if E is perpendicular to A, then EA cosine theta is just 0. So then really all we have to do is we have to look at the surfaces where our electric field is parallel to A. And then we also have to choose a surface so that the electric field always has the same value at all points. And that's going to be maybe sometimes a little trickier to picture. And when you do that, then this equation just simplifies down to EA is equal to Q enclosed over E naught. And that is our goal, to simplify it down even further. So here's how we solve Gauss's law problems. We draw the charge distribution, we draw some field lines for it. We choose a Gaussian surface so that the electric field is either constant or 0 at all points on the surface. We sketch some A vectors, some surface area vectors near those electric field lines so we can figure out if they're parallel or perpendicular. We write Gauss's law, and then we simplify with the symmetry. And then we determine the surface area of the Gaussian surface. That's the A in the EA. And then we determine the total charge enclosed. And once we do that, we solve for whatever it is that we're looking for. So we're going to do this for a point charge, because we actually already know the electric field of a point charge. So we're going to start with a positive point charge Q. And we want to find the electric field as a function of R from a point charge. So as we go further and further from the point charge, we want to be able to calculate what is our electric field at any one point, anywhere in this field. So the first thing we need to do is draw our charge distribution and sketch representative field lines. Ta-da! Which we've done. The next thing we want to do is we want to choose a Gaussian surface that is symmetrical. Well, we already showed that a very symmetrical charge distribution is going to be a sphere. So I'm going to draw a sphere that has a radius of lowercase r. And that is going to be very symmetrical. It also is going to have the same electric field strength because the electric field gets weaker the further away you are from that point charge. So then we can sketch the representative A vectors, so we can choose a couple of points along the surface for that. So I picked this little spot over here, and that's going to point out and away, and I picked this little spot right here, and that's out and away. And we can see that no matter where I pick my little part of the surface to analyze, my electric field is always going to be parallel to that. And my field lines are always exiting. So we can write Gauss's law, then simplify. So we need to add up the EA cosine thetas for all surfaces. Well, hey, this has one surface, the outside of the sphere. So we can simplify that to EA because our electric field is always parallel along the surface of this sphere. So EA is equal to Q enclosed over E naught. And then we want to determine the surface area of the Gaussian surface in terms of the defined variables. Now on your formula sheet there is a geometry section which has the surface areas of common shapes such as cylinders, rectangular prisms, spheres. So if you were to look on that formula sheet, you would find that the surface area of a sphere is 4 pi r squared. And then we need to determine the total charge enclosed by the Gaussian surface. This one's also not that bad because it's just equal to Q because we're enclosing all of Q. So then we substitute these into Gauss's law. So we're substituting an A and Q enclosed. So our A was 4 pi r squared. So I make sure to use the parentheses to show that I'm doing a direct substitution. And then I'm substituting in a positive Q for Q enclosed. And we want to solve for the unknown. So to do that, I need to get, we're looking for E, so we need to get E by itself. So we divide the 4 pi r squared to the other side. So we get E is positive Q over 4 pi r squared times E naught. Now, this doesn't quite look like what we did before. But if we do a little arranging, we can actually see we get the same answer that we did by using our definition of the electric field in Coulomb's law. So I can pull out the 1 over 4 pi E naught, leaving the Q over R squared on its own. And then K is 1 over 4 pi E naught. So this is just E equals KQ over R squared, which was the electric field due to a point source charge. And why this may feel like a lot more work, which it is, if we did not already Coulomb's law. So for situations where you don't have an equation for force, you cannot do that the electric field is the force over Q0. Gauss's law is a way to make this happen. All right, let's look at a conceptual example. So we have two spheres. One has a radius r and the other has a radius of 2r that are drawn around a single charge, positive Q. Which of the following statements about the net electric flux of the two surfaces is true? Think about it. Pause the video. When you're ready, unpause and we'll go over it. All right, so there's a lot of things to think about with our flux. So our flux is based on our enclosed charge. And And since our enclosed charge is actually the same for both, we're enclosing a charge of positive Q, we actually get the exact same value. Now, why does this work? So each circle has the same number of field lines exiting the surface. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have the same number of field lines. So our electric field is different at the two surfaces, though. So our electric field is proportional to 1 over r squared. Okay, we know that because our E is kq over r squared. So even though they have the same number of field lines, the electric field is actually weaker further out. The surface areas are also different because our A is 4 pi r squared. The r that is further out is proportional to r squared, but has a weaker electric field proportional to 1 over r squared. So since our flux is E times A, the r squared for the A and the 1 over r squared for the E actually cancel out, giving us the exact same flux. But this was a lot easier with Gauss's law, because Gauss's law states that the net flux is proportional to the net enclosed charge. And since the net charge is the same in both cases, our flux is the same in both cases. Two different ways to explain the same answer. So coming back a little bit to our conductors and electrostatic equilibrium, we know that there is no net motion of the charges inside the conductor. Okay, we talked about this. There's no electric field in the center because the electrons are repulsing and arranging themselves so that the net force is 0 and the electric field is 0. So our electric field inside any conductor must also be 0. So this is true if you're using Gauss's law. If this wasn't the case, then our charges would have a net force and they would be moving. We also know that any excess charge must reside on the outside surface of the conductor. So we can apply Gauss's law by creating a Gaussian surface inside the material of the conductor. When this happens, the electric field is 0, so there's no net charge inside the Gaussian surface. So let's take a look. This blue area is the material of a spherical conductive shell. So picture like an empty sphere, a hollow sphere. But the blue is our conductive metal. So we create a Gaussian surface that is that blue line that is inside the conductor. The electric field inside the conductor is 0. So since our electric field is equal to being Q enclosed over E naught, our electric field is 0, which means our Q enclosed must also be 0. So there is no net enclosed charge. Okay, well that makes sense if there's nothing going on here. So no enclosed charge inside of here. If it's neutral, then it's got equal numbers of protons and electrons. All right, makes sense, right? No enclosed charge, no electric field, all works. But this does not have to be a symmetric case. There can be all sorts of weird things going on. It could be a wibbly wobbly surface. One of my favorite questions has some like weird wibbly wobbly surface here. And if you create a Gaussian surface that looks like this, if we're inside of the conductor, hey, our electric field still has to be 0 and we have to have no enclosed charge. So it doesn't have to be a nice perfect sphere like that. Just we tend to use these spherical charge distributions because they're a little easier for us to handle. So now, this is going to be true. If there's an empty non-conducting cavity inside the conductor, okay, this is non-conducting, it's empty, then the electric field is still 0 inside that conductor. Okay, all right, nice. You just told me 3 times that there's no electric field inside. Why are you doing this? Okay, well, what happens now if I stick a positive charge in that hollow part? So the blue ring still is our medical spherical conductor. Now I've got a positive charge in there. So what happens is this positive charge is going to attract an equal negative charge because my neutral conductor still has positive and negative charges in it. So picture that we've got all these positive and negative charges inside. Well, what happens is we're going to pull negative charges. These negative charges are going to get pulled towards the center. They're not going to leave the conductor. They're just going to move towards the surface. So leaving our positive charges in place. So the positive charges all stay in place. But now we've got negative charges on that inside surface. And when I said we picture that they're at the surface. So what ends up happening is the positives we then picture as being outside the surface. They're not actually outside the surface. You know, I drew my positives on the inside, but there is still a net positive charge on the outside of that surface, which is what this is showing. So you have a negative Q's worth of charge inside because that's how much charge is going to be attracted towards the center. That's going to mean we're going to have a positive Q's worth of charge outside because my conductor still has to be neutral, which means I still need to have a total amount of charge that adds up to 0. So my conductor has now become polarized. So if we construct that same Gaussian surface that is on that inside surface, it is still inside the material. It's in the blue section, right? It's in the blue side. It's in the metal material. There is still no net enclosed charge because what's being enclosed is the positive Q and the negative Q. So our net enclosed charge inside of that blue dotted Gaussian surface is still 0. So the electric field inside the conductor, and I could put that guy here too. I could put that Gaussian surface anywhere inside that blue material and my electric field is still going to add up to 0. So our rule that the electric field inside of a conductor is equal to 0 is true in all cases. But there'll now be an electric field outside, and so there'll be an electric field emanating outside that was not there before. So if I was to put a Gaussian surface out here, I would be enclosing a positive Q's worth of charge because I've got a positive Q, negative Q, positive Q. The positive and negative for the conductor cancel, leaving me with still that enclosed positive Q. So that neutral conductor doesn't hide the charge from the world, but it redistributes the charges so that electric field is still detected. So it's kind of cool, all due to that polarization of that conductor. So cool things happen as a result of that. If you've ever been to some of the like science museums, they'll sometimes have these big Van de Graaff generators that they'll put on like electric light shows. This is a Faraday cage. There's actually a dude inside of that cage. The cage protects the guy inside from the lightning being created by those electrostatic generators. So we could use Gauss's law to prove a lot of different things. But we do know that the electric field just outside a charged conductor must be perpendicular to conductor surface. Otherwise, if the field was parallel, the charges would be accelerating along the surface. And the magnitude of the electric field just outside of a conductor is equal to sigma over E naught, where sigma is the local surface charge density. So it's the surface charge divided by the surface area. This could be found using Gauss's law. When I teach this as a calculus-based course, we actually go through and derive this and prove that this is actually true. So if you were to say have that spherical conductor that is right here, it's going to have a surface area that is equal to 4 pi r squared. If there is some sort of surface charge, so I've got that positive Q on that surface from the previous example, that would be my surface charge. That would be a positive Q over my surface area of A. So basically what this would allow me to find is it would allow me to find my electric field using Gauss's law, because my sigma here would be Q over A, and my electric field is equal to sigma over E naught, and that is always going to be true. So this tells me that if I were to sub in, then sigma is Q over A all over E naught. So this gives me E is equal to Q over A times E naught. And that A, for example, would be our 4 pi r squared, Q over 4 pi r squared E naught. And actually what we're going to find is like the spherical conductor actually behaves just like a point charge, because this is the same thing as what we found with Coulomb's law for a point charge. So kind of cool.